Hello, let's see you again, and let's start our lecture on on avionics engineering. And today we have lecture number 4. The lecture topic is computer-aided optical design. You know, the use of computer-aided optical design methods has been referred to earlier and is briefly discussed in this section of our lecture to show its importance. None of the modern HUDs and HMDs, in fact, would have been visible without it. Modern optical design software enables very sophisticated, because sounds better than complex, optical design to be optimized and the performance determined. For example, ray tracing for an optical terrain, including the center and tilt optical elements. Aspheric elements and holographic elements can be carried out. An automatic optimization program can be carried out iteratively, whereby the curvature of all the individual elements, their spacing, tilt, decentering, refractive index, can be varied to seek an optimal solution using hill climbing method. This enables the optical designer to evaluate a very wide range of configurations to achieve the performance goal. These programs take several hours to run even on the most modern mainframe computer. And this slide shows a computer-generated ray trace for a wide FOV holographic HUD as an example of the optical complexity involved in such design. I hope you remember our abbreviation, what means FOV, okay? So it also allows quick feasibility studies of a range of optical configurations to be run. There are, of course, many more optical analysis functions which can be carried out using modern optical design software, but space constraints limit further discussion. And now we became to third topic of today's lecture, discussion of HUDs versus HMD. The current and future roles of the HUD and HMD in military aircraft will be discussed in a nearest section. The question of HMD for civil aircraft application does not arise as civil airlines pilots have no need to wear helmets. The pilot's communication requirements are met by a simple cushion headset with attached microphone. The acoustic noise level in the civil aircraft are much lower than in military aircraft, and the head protection requirements do not arise. Okay? An oxygen mask is only required in the event of the loss of cabin pressurization, whereas the helmet forms part of it. A special oxygen breathing system for high G maneuvering in combat aircraft. Next topic is military aircraft HUDs and HMD. The ability of the HMD to display all the information that is displayed on the HUD over a wider FOV, which is not confined to the forward sector, arises the question of whether the HUD will still be necessary in the future. The answer is that the HUD is likely to remain a key system for some considerable time as prime displays of primary flight information to the pilot, and to enable high accuracy weapon aiming with guns, ingredient bombs, and rockets to be achieved. Dealing first with the question of integrity, the display of primary flight information must meet an integrity figure of 10 in power minus 9 for the probability of occurrences of displaying potentially misleading or hazardous information. A single unit HUD system, combined processor, symbol, generator, and display, can meet this integrity figure using the monitoring techniques described a bit further. The HMD system, however, is not a one-box system and comprises helmet, cockpit interface unit, head tracker, and processor or symbol generator, which are all dispersed around the cockpit and require a relatively large number of connectors. Critically, the need to minimize the head reported weight result in the CRT drive circuit can be located remotely from the helmet, at least at the end of an umbilical cable. Such a widely dispersed architecture cannot achieve as high an integrity as a single unit HUD system. The integrity issue, however, is not an insuperable one, with the advances being made in display technology and the incorporation of adequate redundancy and monitoring into the system. Clearly, the integrity of the display of primarily flight data, such as attitude information and heading on the HMD, is dependent on the correct function of the head tracker system. It appears feasible to devise self-monitoring techniques to check the integrity of the head tracker system. Alternatively, a dual tracker system would be installed as monitor or used in conjunction with a self-monitoring system. An alternative get-you-home source of attitude could be obtained from a triad of miniature solid-state gyros and accelerometers mounted directly on the helmet, and coupling the helmet attitude from there out. Dealing next with the question of accuracy, the HMD is entirely adequate for launching precision-guided weapons, such as missiles and laser-guided bombs. These weapons are highly effective, so why is very high accuracy still required for weapon aiming? The answer is that guided weapons are highly expensive, and in today's scenario of cost limitation, iron bombs, rockets, and guns come cheaply. Despite of efficiency of beyond visual range, BVR, beyond visual range, missiles, the difficulty of identifying friends from foe still exists, and the near in use of guns is still considered necessary. It is not feasible to target unguided weapons with an HMD to the same accuracy as with HUD. HUD accuracy is derived from a chain of elements comprising input data, processing and symbol generation, analog deflection and video, cathode ray tube installation. All these factors have now become highly sophisticated to the extent that the final element in the chain, the pilot, gives equal or greater error. Overall, from the data input to HUD optical output and accuracy of better than 105 up to 1 millirad can be obtained from placing a symbol over the target at the center of the field of view. Even at the edge of a typical refractive HUD, at 10 degrees of axis, a figure of 1.5 up to 2 millirad is achievable. The HUD is rigidly attached to the airframe and aligned to a fraction of a millirad by mechanical and electronic means. The alignment of optics and CRT also benefits from the rigidity of the HUD chassis, such that the port side error can be as low as 0.15 millirad to pitch and yaw, and up to 0.6 millirad in roll. The HUD is equally in a fixed relationship to the windshield and views the outside wall on only through a small and well-defined segment. Corrections can be readily applied in respect of windshield optical effect and symbol position distortion. Conversely, the HUD cannot be as rigidly located with respect to the pilot's eye because of limitations of helmet design, such as eye relief, weight, comfort, etc. The pilot's line of sight with respect to the airplane axis has to be inferred by the head tracker, and also accuracy on the board side and in the principal region of the head motion box is better than 2 millirad. And this degrades to 10 or up to 8 and up to 10 millirad at large of board side angle. It is also affected by the ability of the pilot to hold its head steadily under the buffeting experience at a high subsonic speeds in turbulent conditions. The advent of a practical eye tracker may eventually exchange the operational accuracy of the HMD. A further difficulty with the HMD is that it is not easy to compensate for windshield error to a very high degree of accuracy over the whole head motion box. The end-to-end accuracy chain for the HMD will, in addition to the HUD factor, and has 3 additional factors: helmet alignment, tracker accuracy, and windshield. This slide shows the accuracy relationship to off-board sight angle for the HUD and HMD. The current limitation of the HMD in terms of unguided weapon delivery accuracy can be seen. Development is being carried out to improve head tracking accuracy, and it should be possible to achieve an acceptable accuracy, albeit not as good as the HUD. The degradation in HMD aiming accuracy encountered in the aircraft experiences severe buffeting in high-speed low-level attack has been mentioned and is constant. The cost, weight, and cockpit real estate savings, which can be made by eliminating the HUD in the fighter or strike aircraft, have provided a strong incentive to improve the integrity and accuracy of the HMD system. The weight and bulk of the HMD must also be made as low as possible. It is interesting to note that the new Lockheed Martin Lightning II Joint Strike Fighter does not have a HUD and relies entirely on the HMD. The new technology HMDs and HUDs that will be described in future modules, which explore holographic wave-guided technology, however, offer lower cost, lower weight, and better performance than the current technology system. It may thus be possible to justify having both a HUD and HMD with this new technology. This is because of the inherently higher accuracy of the HUD provided for delivering unguided weapons and the increased integrity of displaying primary flight information, which two independent systems can provide. The existence of laser devices which can cause eye damage has been in the public domain since the early 1980s. These can be operated at relatively low power levels to dazzle the pilot of an approaching aircraft, so that the pilot becomes disoriented and has to brake all the time. The laser can also be operated at higher power levels, which are sufficient to cause permanent damage to the retina of the eye, resulting in impaired vision and blindness if sufficiently high. In future conflicts, it may therefore be necessary to fly with a suitable opaque visor installed on the helmet to protect the pilot's eye from optical weapons when operating in areas where such a threat exists. The pilot would then fly the aircraft by means of head-steered indirect viewing system with overlaid flight and weapon aiming symbology. The potential of the HMD and the exploitation of virtual cockpit concept has already been briefly discussed, and it is likely that such concepts will be exploited in the next generation military aircraft. Finally, it should be noted that there are several applications for the HMD as part of an indirect viewing system for night and all-weather operation of helicopters. This includes air-sea rescue operations, servicing offshore oil rigs, police helicopter surveillance, and border patrols using helicopters. Next topic today's lecture is head-down display. Electronic technology has exhibited an exponential growth in performance over 4 decades and is still advancing. By the early 1980s, it became viable of effect of revolution in civil flight decks and military cockpits by replacing the majority of the traditional dial-type instruments with multifunction color CRT displays. Wall-to-wall color displays have transformed the civil flight deck from large jumbo jets to small commercial aircraft. The only traditional tile instruments which have been retained are the electromechanical standby instruments, such as the altimeter, airspeed indicator, artificial horizon, and heating indicator. These electromechanical standby instruments, however, are now being replaced by solid-state equivalent with a colored LCD display presentation in the new generation of aircraft entering service or in avionic update program. It should be noted that the current supremacy of the flat panel AM LCD display may well be challenged in the near future by the organic light emitting diode or LED display. Or LED displays were still under development from 2003, so more than 20 years for now. Development problems have been overcome, and high resolution, super thin flat panel color LED displays are commonplace in mobile phones and are appearing in top of the range TV sets. LED displays have a number of significant advantages over AM LCD. They are an emissive display with an inherently wide viewing angle, and crisp display characteristics. They have a fast response time of 10 to 20 nanoseconds and have a wide operating temperature range when properly packaged. They have active matrix addressing like AM LCDs and can have high brightness. They are thin and do not require an illuminating light source like the MA LCD, and thus enable a slim flat panel display to be achieved. Typically, the HDD comprises the display together with the drive electronics and power regulation. As with the HUD, there is frequently a simple processor and housekeeping software to control the brightness, self-test, and mode changes. Some units now contain a full processor and symbol generator and database bus interface, but it is more usual for the HDDs to be driven by a central display processor. The size of an HDD is typically defined by an ARINC standard of square format with 1-inch increments, for example, 5 times 5.6, 5 times 5 or 6 times 6 inch. And this is not ideal for the normal 4:3 aspect ratio video. And indeed, rectangular format displays are found in both military and civil cockpits. This slide shows a modern civil flight deck. The displays are duplicated on the captain and second pilot and being multifunction. It is possible to reconfigure and display information in the event of the failure of a particular display socket. The electronic primary flight display, PFD, replace 6 electromechanical instruments: altimeter, vertical speed indicator, artificial horizon or attitude director indicator, heading or compass indicator, and Mach meter. PFD format follows the classic T layout of the conventional primary flight instrument. And this figure shows a representative primary flight display. Airspeed is shown on a scale on the left with pressure attitude and vertical speed on the right-hand scale. Aircraft heading information is shown on a tape scale type format below the attitude display. The artificial horizon or attitude display has a blue background above the horizon line representing the sky and the brown background below the horizon line representing, you understand, yeah, right, ground. And this enables which way is up and the aircraft orientation to be rapidly assimilated by the pilot in recovering from an unusual attitude. For example, as the result of a severe jet upset. It should be noted that the attitude direction indicator is the key display on any aircraft for recovering from unusual attitudes, particularly when the normal outside world visual cues are not present, like flying in clouds or at night. Okay? As pilot can become disoriented, the normal displays of attitude on the HUD is not suitable for this purpose, being to find a scale which consequently moves too rapidly. And this slide shows a typical navigation or horizon situation display. Pilot selectable modes include the traditional compass rules, hidden display, expanded ILS or VOR formats, a map mode showing the aircraft position relative to the specific viewpoints, and the north-up mode showing the flight plan, where the radar displays may be superimposed over the map, and the vertical flight profile can also be displayed. This slide shows an engine warning display. And the next figure shows a system display for monitoring the aircraft system. For example, the fuel system or hydraulic, electrical system, air conditioning, and other systems showing current status. All the HUD functions may be repeatedly overlaid on this part of our lecture. Fuel and engine data, navigation waypoints, and host of housekeeping functions like hydraulics, pressurization may be displayed. A store's management display is also required, showing the weapons carried and their status. It is usual to have a bezel around the display with keys. Sometimes key functions are dedicated, or they may be soft keys where the function is written beside the key on the display. So-called tactile surfaces are being introduced using such techniques as infrared beams across the surface of the display, or even surface acoustic waves, where the pressure applied can also be measured to give X, Y, and Z coordinates. Typical advanced military cockpits are configured with 4 head-down displays. There are 2 large color displays: a horizon situation display, HCD, providing a 6 to 8 inch map display in portrait format with symbol overlay of routing and thread data, and vertical situational display VSD, providing an 8 to 6 inch infrared video display showing targeting video at various magnifications. The other 2 displays are smaller 5 to 5 inch monochrome displays comprising a system status display, SSD, displaying system status data, and system control display, SCD, displaying system control data. Both displays have tactile data entry overlay. The advanced cockpits for the new generation of fighter or strike aircraft have just 2 large color displays as the primary head-down display. And this figure shows the instrument panel of the Lockheed Martin Lightning II Joint Strike Fighter, which features 2 large flat panel color display surfaces. The pilot can divide each screen into several windows, as can be seen in the illustration, enable a very wide variety of information to be displayed at the same time. These flat panel displays are the same type as used in commercial laptop computers and are hardened to withstand the fighter environment by mounting them in rugged vessels. And now next topic of today's lecture is display symbology generation. Symbology such as line, circles, curves, tiles, scales, alphanumeric characters, tabular information, map display features is drawn as a set of straight line segment approximation, or vectors like a join the dots, children's picture, and so on. The system electronics use commercial off-the-shelf graphics processing chips, frame stores, and display drive processors developed for video games, PCs, etc. Next subtopics today lecture: digitally generated moving color map display. A map is by far the best way of visually assimilating the aircraft's horizon situation. That is the position of the aircraft relative to the chosen wayview points and destination, alternative routes, targets, and locations of specific terrain features such as mountains, hills, lakes, rivers, coastline, towns, cities, railways, roads, and many, many others. Color map can now be generated digitally from a map database stored in the computer memory and moved in real time with the aircraft, so that the aircraft is at the center of the map display. And the map can be oriented track up or north up by selecting the appropriate move. The navigation system provides the basic information to move and rotate the map to maintain the selected orientation, but usually track up. The system has major advantages in flexibility and the ability to present and overlay information, which is not possible with the earlier projected field map display. Some of the advantages are scale flexibility. In this case, the map can be displayed at any selected scale. The time to redraw the map at the new selected scale is typically 1 to 2 seconds. Look ahead and zoom facility. The pilot can look at the map some distance ahead of the aircraft, present position, and zoom in at the large scale to see the terrain details, for example, in the target area or destination airfield. Terrain clearance display. The terrain above the pilot's present altitude can be distinctly colored so that the pilot is aware of the location of potentially dangerous terrain, such as the hills and mountains relative to the aircraft. Appropriate avoiding action can then be taken in good time. Terrain screen display. The areas below the radar LOS of known or likely enemy radar sites can be displayed on the map, so that advantage can be taken of terrain screening or minimize the probability of detection. Decluttering, features and information like place names, which are not required, can be deleted from the map display to decluttering. To declutter the map for a particular phase of the mission. Specific features can also be emphasized. The map display can be restored to show the full information whenever required. Threat locations, and these may be enemy missile sites, AAA sites, fighter airfields, or radar. Threat enveloping, showing, say, the missile range from a particular site or sites, and can be shown in distinct colors. Known low altitude obstructions. Electricity pylons, power cables, towers, etc. can be emphasized on the map, for example, by brightening them up when flying at low altitude. 3D map displays. A 3D map can be generated of, say, the target area to assist the pilot in visually assimilating the local terrain and hence assist in target acquisition. These slides illustrate digitally generated video map displays. The information to construct the map is stored in a digitally database, a set of the specific terrain features such as coastlines, rivers, lakes, contour lines, town outlines, railways, roads, woods, airfield, electricity pylons. The feature outline is specified as a set of vector coordinates, which form straight line segment approximation to the feature outline. The color and fill for the feature is also specified in the data. Map databases which are stored in this way are known as vector databases. The method gives an extremely powerful means of data compression to enable all the information depicted on a map to be stored in a practical size of computer memory for airborne application. The map can easily be decluttering by deleting a particular feature set from the display. The task of compiling a worldwide mapping database is a continuing activity by the various mapping agencies around the world, but is clearly a major task. There are vast areas where accurate ground survey data are not available, and the map data has to be derived from surveillance satellites. The task of drawing a map and translating and rotating it in real time with aircraft motion is a major processing task, but can be readily accomplished with modern electronics hardware and now available. Microprocessors, graphics chipsets, semiconductors, memory devices, etc. Typically, the map data allocated into a frame store which hold the data for an area whose sides are 1.4 times the size of the map area being displayed. Scrolling the map display is illustrated in this figure. Map rotation is accomplished by rotating the addressing of the frame store as shown in this figure. The frame store size of 1.4 up to 1 and covers the fourth case heading changes. Another topic today's lecture, solid state standby display instruments. Until recently, the standby instruments which provide primarily flight information to the pilot in the event of loss of main displays were all electromechanical instruments. These are very well proven and reliable instruments, having been progressively developed and improved over many years. The cost of ownership of electromechanical instruments, however, is relatively high and is increasing as there is a high skilled labor content in their repair and maintenance, together with the need for high standard clean room facilities. This is because these instruments depend on very low friction precision mechanisms, and in the case of gyroscopic instruments, there is also inevitable wear and deterioration in the spin axis bearing system. The skilled instrument technicians required to service and repair these instruments are also a declining group and are not being replaced by a large as new technology no longer required their skill. The technology now available has made it possible to produce an all-solid state equivalent instrument with a color AM LCD display, which is a form, fit, and function replacement for the electromechanical instrument or instruments in some cases. The solid-state equivalent instrument is packaged in a standard instrument case or housing and uses the same electrical connector interface. The initial cost of this instrument is competitive with the electromechanical version, but more importantly, they offer a tenfold improvement both in reliability and cost of ownership. This is because of the inherent reliability of solid-state sensors, with no wear or degradation mechanism in their operation. They incorporate very comprehensive built-in test and monitoring, and repair is affected by replacing modules and the use of automated testing facilities. Highly skilled instrument technicians and clean room facilities are not required. That's very nice. I hope you agree with me. And the instruments are also of higher accuracy because of the use of solid-state sensors and the ability to apply complex corrections using the embedded microprocessor. Electromechanical instruments are limited in the complexity of the corrections which can be made. A recent development is to replace the standby attitude indicator, standby altimeter, and standby airspeed indicator with a single solid-state integrated standby instrument system packaged in a 3 ATI case. And this figure illustrates a typical solid-state integrated standby instrument system displaying attitude, altitude, and airspeed. This integrated standby instrument system comprises a triad of orthogonally mounted solid-state rate gyros and accelerometers, and solid-state pressure transducers together with an embedded microprocessor and color AM LCD display and drive electronics. The microprocessor computes the aircraft attitude from the gyro and accelerometer outputs and altitude and airspeed from the pressure transducer output. The system operates from the 28-volt supply, which is supported by the emergency battery. The integral power conditioning electronics are designed to cope with the variations in the battery supply voltage. Next topic, called data fusion. Data fusion is the name given to the process of combining the data from a number of different sources to provide information which is not present in the individual sources. For example, a synthetic 3D picture can be derived of the terrain in front of the aircraft from an accurate terrain database and accurate information on the aircraft position and attitude. The aircraft position and attitude information are provided by GPS and INF or GRM system and INF. The synthetic picture of the terrain can be overlaid one-to-one with the outside scene derived from the FLIR sensor and displayed on an HUD or a head-down display. Ground features which may be hard to detect on the FLIR, such as ridge lines, can be accentuated together with electrical pilot. This enables the pilot to continue visual flight in conditions of marginal visibility, where normally it would be necessary to pull up and fly at a higher altitude. This figure illustrates a display enhanced by data fusion. It is appropriate at this point to discuss alternative ways of displaying primarily flight information, and guidance which are being evaluated in both the USA and Europe. Such displays are sometimes referred to as 3D or 4D displays of pathways in the sky. These displays provide a pictorial presentation of the aircraft's spatial situation and flight paths using synthetically generated ground imagery and explore data fusion. The presentation of primarily flight information on color head-down displays by a large follows the format established by the blind flying panel of electromechanical instruments in the classical T layout. All pilots learn to fly using this primarily flight information format, and its retention in color head-down displays have enabled their acceptance to be achieved in a smooth and straightforward manner with a very little learning curve required. Right? I hope this is one of the interesting aspects. The display of information, however, in any applications involves a process of abstraction, and the mental translation is required to build up a situational awareness and mental picture of what is happening. The objective of these new pictorial displays is to provide the pilot with a more intuitive, a natural appreciation of the situation in terms of the aircraft state, its actual flight path, and the desired flight path with respect to the outside world. This figure illustrates a 3D pathway in the sky display as an example of a military strike mission display. There is a very large number of viable display presentations for civil cockpits, and reaching general agreement on the most suitable will take time. It is clear that a more easily assimilated pictorial type display presentation can be produced compared with the present symbolic presentation of flight and navigational information. It would seem reasonable to predict that these new pictorial presentations will be adopted sometime in the nearest future. To generate these pictorial displays is not a problem with the technology now available. And there is, however, a big difference between demonstrating an experimental system, and the development of a production system approved by the Air Worthiness Authority. The cost involved in the achieving certification by the civil airworthiness authorities is a significant sum, as with any airborne system. The software is safely critical, and the flight trail approve the system do not come cheaply. We could nevertheless have such displays nearest tomorrow if the need was agreed. And next subtopic today's lecture, intelligent display management. The exploitation of intelligent knowledge-based systems, IKBS technology, frequently referred to as expert systems, to assist the pilot in carrying out the mission in the subject of a number of very active research programs, particularly in the United States. One of the US programs is the Pilot Associate Program, which aims to aid the pilot of a single-seat fighter or attack aircraft in a similar way to the way in which the second crew member of a two-crew assist aircraft assists the pilot. The prime aim is to reduce the pilot workload in high workload situations. Space constraints do not permit more than a very brief introduction to this topic, which is of major importance to the next generation of military aircraft. And this will use a single pilot to carry out the tasks which up to now have required a pilot and navigate a weapon system officer. The exploitation of IKBS technology on the civil flight deck will allow as the technology becomes established in military applications. A subset of all the proposed expert systems on the aircraft is an intelligent displays management system to manage the information which is visually presented to the pilot in high workload situations. It is the unexpected or uncontrollable that leads to an excessive workload, examples being the bombs or interception by counter-attacking aircraft with very little body. Evasion of ground threat like surface air missiles, bird strike when flying at a low altitude, engine failure, weather abort or weather diversion emergency. A block diagram illustrating the concept of an intelligent displays management system is shown in this slide. The system comprises an aircraft state expert, which deduces what is happening from the aircraft data, pilot inputs, threat warning system, and the mission plan by the application of an appropriate set of rules. The aircraft state expert in turn controls the displays management expert, which determines the information displayed on the various display surfaces, HUD, map, head-down display, or HMD, according to an appropriate set of goals and priority rights. Our next lecture, it will be computer-aided optical design. I think it's enough for today. Okay, I hope you enjoyed this lecture, and I'm looking forward to see you next time. Bye.